Multi-degree of freedom mechanical systems are represented by ordinary differential equations expressed in matrix form. Initially, we will study undamped systems that are represented by the matrix equation mx double dot plus kx equals f of t. The vector x of t is an n by 1 vector of generalized displacements, where n is the number of degrees of freedom in the system. The term generalized refers to the fact that these displacements might represent a mixture of linear displacements and angular displacements depending on the problem being studied. M is an n by n mass matrix, and K is an n by n stiffness matrix. F of t represents the externally applied generalized force vector. Note that this equation reduces to the single degree of freedom equation of motion when n equals 1. Expanding each of the terms illustrates the form of the matrix equations of motion. M is comprised of individual elements of mass denoted m sub ij, where I is the row in the mass matrix and j is the column. Likewise, the stiffness matrix is composed of stiffness elements denoted k sub ij. On the right-hand side of the equation is, in general, a matrix of applied generalized forces. Since the system has multiple degrees of freedom, there may be multiple generalized forcing functions that act upon different degrees of freedom in the system. Therefore, we represent the applied generalized forces as an n by p matrix, where p is the number of inputs. Also denoted in this equation is the coupling terms that represent the coupling between different degrees of freedom. For example, a spring that connects the first degree of freedom to the nth degree of freedom will be represented in the stiffness matrix by the term k sub I 1n. In general, the mass matrix also includes coupling terms, although many mechanical systems are modeled as lumped parameter systems, and in these cases, the mass matrix is a diagonal matrix in which each term on the diagonal represents the mass associated with a particular degree of freedom. As we did for single degree of freedom systems, let's start the analysis by solving for the free vibration response of this multi-degree of freedom system. Setting the applied generalized forcing matrix to 0 yields the equation mx double dot plus kx equals 0. We assume a solution of the form u e to the j omega t, where u is an n by 1 vector of undetermined coefficients, and the complex exponential represents a harmonic function of time. Taking the derivative of the assumed solution yields a matrix expression in which the term u e to the j omega t is common. The second derivative of the assumed solution yields a term minus omega squared in front of the mass matrix. The resulting matrix expression is the product of the n by n matrix, omega squared m plus k times the undetermined vector u, multiplied by the complex exponential function. The solution of the differential equation is obtained by solving this matrix expression. First, we assume that the n by n matrix minus omega squared m plus k has an inverse. Under this assumption, we can simply multiply both sides by the inverse of the matrix and, in this case, we find that the only solution is the null solution, u equals 0. This implies that there is no motion in the system, so substituting back into the assumed solution would yield x of t equals 0 for all time. Therefore, this is not a valid solution. Our next assumption is that the matrix minus omega squared m plus k is not invertible, which is equivalent to assuming that the n by n matrix in the brackets is singular. Rewriting the matrix as k minus omega squared m, we note that the determinant of a singular matrix is equal to 0. Expanding out the determinant of the matrix yields an nth order polynomial in the term omega squared. Solving for the roots of this polynomial will yield n values of omega squared. Generally, these are then ordered from omega 1 squared to omega n squared, where omega 1 squared is less than omega 2 squared, and so on. Assume that the values of omega squared have been obtained by solving for the roots of the polynomial shown on the previous chart. The undetermined vector of coefficients u is obtained by substituting this result back into the matrix expression k minus omega squared m times u equals 0. For each value of omega squared, denoted omega sub I squared, there will be a corresponding vector u sub I which solves the matrix expression. Now we have to call upon some matrix algebra theory to help us solve for the vector u sub I. Since a matrix k minus omega sub I squared is singular, we recall that the columns of a singular matrix are linearly dependent. This means there is an infinite number of solutions u sub I that solve the matrix expression. The easiest approach to solving for the vector u sub I is to choose one element of the vector, say the first element, and compute the remainder of the elements in the vector. Since this vector is not unique, it can be multiplied by any non-zero number and it will still remain a solution to the matrix expression. Once the values of omega I squared and the corresponding vectors u sub I have been determined, they can be substituted back into the assumed solution of the original differential equation. Since this is a linear differential equation, each value of omega sub I squared and u sub I is a solution to the differential equation. Therefore, the total solution to the free vibration problem is a linear combination of each individual solution parameterized by omega sub I squared and u sub I. The complex exponential term can be rewritten as a harmonic function with a frequency omega sub I and a phase angle phi sub I through the Euler transformation. Thus, the solution to the differential equation is a linear combination of harmonic functions of time multiplied by the vectors u sub I and an undetermined amplitude a sub I. This result is one of the most important results in linear vibration theory. It says that an undamped multi-degree of freedom system will vibrate as a linear combination of modes, where the ith mode is parameterized by the ith natural frequency omega sub I and the ith mode shape u sub I. The natural frequency defines the vibration frequency of the mode, and the mode shape defines the relative size of the generalized displacements when they vibrate in that mode, hence the name mode shape. The final step in solving for the free response of the system is to determine the amplitude and phase shift of each mode of vibration. As we did with the single degree of freedom systems, the amplitude and phase shift is computed from the initial displacement and initial velocity. For multi-degree of freedom systems, there is an n by 1 vector of initial displacements and an n by 1 vector of initial velocities. Setting t equals 0 in the assumed solution and setting the term equal to the initial conditions yields a set of 2n equations in 2n unknowns. This set of equations can then be solved to determine the undetermined coefficients a sub I and phi sub I. Once these are determined, the solution is complete. Now let's look at a 2-degree of freedom example to gain a better understanding of how we solve for the natural frequencies of a multi-degree of freedom system. Consider a general 2-degree of freedom system with a fully populated stiffness matrix and a diagonal mass matrix. As discussed earlier, the diagonal mass matrix is indicative of having a lumped parameter model of the 2-degree of freedom system. Finding the expression for the natural frequencies of the system requires solving for the determinant of the matrix K minus omega squared m. Using the matrices defined in the previous chart, we can write the 2 by 2 matrix K minus omega squared m. The non-invertibility of this matrix is equivalent to stating that the determinant of the matrix is equal to 0. Expanding the determinant using the formula for the determinant of a 2 by 2 matrix, we see that the resulting expression is, as expected, a quadratic function of omega squared. The polynomial can be manipulated to yield an expression in which the coefficient of the omega to the 4th term is equal to 1. Since this is a quadratic expression in omega squared, the quadratic formula can be used to obtain both solutions for omega squared. Direct application of the quadratic formula results in the first expression on this chart. The expression can be simplified a little bit by expanding the terms and combining the result with the second term in the square root. The remaining term can then be simplified again as the square of the difference between k22 over m22 and k11 over m11. Now at this point in the solution, it's always good to examine the result and see if it makes sense under certain conditions. We note that if the cross-coupling term k12 is equal to 0, then the solution of the quadratic formula reduces to two solutions, k11 divided by m11 and k22 divided by m22. You'll recognize these results as the natural frequencies of the decoupled 2-degree of freedom system. This makes sense since the term k12 serves to couple the vibration of the 2 degrees of freedom. If this coupling was 0, the two masses would oscillate independently at frequencies defined by their individual mass and stiffness. To understand how to compute the natural frequencies and mode shapes for a particular system, consider the two mass spring system shown in this figure. The values of the masses are 9 kilograms and 1 kilogram respectively, and the two stiffness values are 24 newtons per meter and 3 newtons per meter respectively. Using Newton's second law to obtain the equations of motion results in the matrix expression shown at the top of the chart. The mass matrix is a diagonal matrix, while the stiffness matrix includes a non-zero coupling term. This coupling term represents the stiffness of the spring that connects mass 1 to mass 2. We can use the general expression derived earlier by noting that M11 is equal to 9, M22 is equal to 1, K11 is equal to 27, and K22 is equal to 3. The coupling term K12 is equal to -3. Substituting these values into the general form for the solution, we can solve for the two values of omega squared. The term under the square root simplifies because the two terms cancel one another out, and the solution is equal to 1/2 times the term 6 plus or minus 2. This results in two values for the square of the natural frequency, 2 and 4. By convention, we define omega 1 to be the smaller of the two values. Taking the positive square root of each value yields omega 1 equals square root 2 radians per second, and omega 2 is equal to 2 radians per second. These are the two natural frequencies of the undamped 2 degree of freedom system. We can solve for the first mode shape by substituting the value of the first natural frequency squared back into the matrix equation K minus omega 1 squared m. The result is a 2 by 2 matrix. The product of this matrix and the first mode shape U1 is equal to the 0 vector. Recall that the determinant of this matrix is 0. You can check your calculation at this point by confirming that the matrix is indeed singular. You can see from the bottom equation that the two columns of the matrix are linearly dependent. If they were not, then this indicates that a mistake has been made in the computation of the natural frequency or in the computation of the matrix K minus omega 1 squared m. An equivalent check is to confirm that the determinant of the matrix is 0 when omega 1 squared is substituted back into the matrix. You can see from the equation above that this is the case. Continuing with the solution, we write out the two equations defined by the product of the matrix with the undetermined vector u1. Since u1 is not unique, we can simply choose one of the values of the vector and solve for the remaining value. In this example, we set the first element of the vector to be equal to 1 and solve for the second element, which in this case is equal to 3. Thus, the first mode shape can be written as shown on the chart. Remember that this mode shape is not unique, so it can be multiplied by any non-zero scalar and it will remain a solution to the original differential equation. The same process can be used to solve for the second mode shape of the system. Substituting omega 2 squared equals 4 into the matrix K minus omega 2 squared m, we once again note that the matrix is singular. Choosing the first element of U2 to be equal to 1 and solving for the second element yields the second mode shape shown at the top of this chart. The two mode shapes are summarized at the bottom. Note that the elements of the first mode shape have the same sign, indicating that both degrees of freedom are in phase when vibrating in the first mode. Conversely, the elements of the second mode shape are opposite in sign, indicating that the two masses will vibrate out of phase in the second mode. The mode shapes can be visualized by drawing a scaled figure illustrating the relative motion of the two masses when vibrating in the first and second mode. For the first mode, mass 2 will vibrate in phase with mass 1 at 3 times the amplitude. In the second mode shape, mass 2 will be vibrating at 3 times the amplitude of the first mass, but out of phase by 180 degrees. When the first mass is moving in the positive direction, the second mass will be moving in the negative direction at 3 times the amplitude.